Hello students. Now in this session we will discuss some important numericals from the topic thermodynamics. Right? So this is one question given. The pressure volume work for an ideal gas can be calculated using the expression W equals to minus PdV integral from V1 to V final, V initial to V final. The work can also be calculated from PV plot. We have studied this. Work can also be calculated from PV plot by using the area under the curve within the specified limits. So we studied this in the concepts. When an ideal gas is compressed reversibly or irreversibly in two ways, from initial volume Vi to final volume Vf, choose the correct option. That is the question given. So reversible work is equals to work done in a reversible compression is equal to irreversible. Reversible is less than irreversible. Reversible is greater than irreversible, or reversible is equal to irreversible plus PdV. Right. Now let us see. So actually, as per the lines given in the question, the work done in this process can be expressed within the limits as see, in this compression is V initial to V final. Even here also V initial to V final. From these two plots, we can understand that area under the curve is greater in case of irreversible compression. Suppose this is irreversible compression. This plot indicates irreversible compression, means it is taking place in infinitesimally slow steps. Large number of infinitesimally slow steps. Whereas here, this is reversible compression. This plot stands for reversible compression. Right. So from these two plots, one can understand that area under the curve is greater in an irreversible compression work than that of reversible compression. So from these two plots, we can say that work done in an irreversible compression is greater than work done in reversible compression within certain limits. So like this, we will discuss another numerical. So this is another question. 1 mole of an ideal gas undergoes a change in state from 2 atmospheres, 3 liters and 95 Kelvin to 4 atmospheres, 5 liters and 245 Kelvin with a change in internal energy 30 liter atmosphere. Right. The change in enthalpy of the process is, then if these are the changes involved in a state as well as in internal energy change, then change in enthalpy can be expressed as, this is the question given. Right. Now we have a relation. We have a relation between enthalpy and internal energy as H equals to U plus PV, pressure volume work. Right. Now enthalpy change H2 minus H1 equals to internal energy change U2 minus E1 plus P2 V2 minus P1 V1 difference. Right. We know final pressure, final volume, initial pressure, initial volume. Now delta H, this is what we have to calculate. Delta H can be calculated as internal energy change. It is 30 plus P2 V2. What is P2? P2 is 4 and V2 is P2 V2 minus what is P1 and V1? 2 into 3. So it is 20 minus 6, 14. So 30 plus 14. So it is enthalpy change is 44 liter atmosphere. So this is how we can calculate a numerical on a relation between enthalpy and internal energy. Let us see one more question based on. So this is another numerical for us from thermodynamics. 6 grams of oxygen gas is expanded so that volume is doubled. 6 grams of oxygen gas is expanded so that volume is doubled. There's work done is, see here, initially it's given with 6 grams of oxygen. See, number of moles of oxygen gas can be calculated as mass of oxygen by molar mass of oxygen gas, that is 6 by 32. It is how many liters? 1 by 4 moles, no? 1 by 4 moles at STP. As 1 mole at STP 1 mole at STP. See here, in this question, we are dealing with STP volume, right? There are two values to confuse us. Old STP conditions and new STP conditions. See, once again I am repeating that one. Old STP conditions are 0 degrees Celsius and 1 atmospheric pressure, whose molar volume is 22.4 liters. New STP conditions according to IUPAC can be given as 0 degrees Celsius and 1 bar pressure, whose molar volume is 22.67 liters, that is simply given as 22.7 liters. We have to remember old and new. Now in this question, of course, in NCERT based examination, volume will be always given accordance with the 22.7 liters. There is no need to worry about this. But in this question, see, options are given in 22.4, 5.6, 5.6, 11.2, means there are multiples of 22.4 are divisibles, right? So we have to follow as 1 mole at STP occupies 22.4 liters. This value we have to take with respect to the options. As 1 mole at STP occupy 22.4 liters, then 1 by 4 moles occupy 1 by 4 moles of oxygen occupy 5.6 liters. This is initial volume of oxygen. This is the initial volume and is expanded so that volume is doubled. As volume is doubled, see, initial volume is 5.6 liters. As volume is doubled during expansion, final volume will be 11.2 liters. Then change in volume will be 11.2 minus 5.6, that is 5.6. Delta V is 5.6. Now work done can be calculated as minus P external into change in volume, that is minus P external minus external pressure is given as 1 atmosphere. See, it is given at STP conditions, no, 1 atmosphere into change in volume is 5.6 liters. So work done in this given question, in this given process is minus 5.6 liters atmospheres. So this is one model question where we can solve it using initial and final volumes. So let us see one more question. So this is another question for us from thermodynamics. An ideal gas expands from initial volume V into vacuum under isothermal conditions. For this process, which option is more suitable? Right. See here, for an isothermal process, delta U, change in internal energy will be 0. Change in internal energy will be 0. We have first law of thermodynamics from first law of thermodynamics. We have delta U equals to Q plus W. So this is 0. Similarly, work done equals to minus P external into dV. We are aware of this relation. As external pressure is 0 in vacuum. So W, work done, is also 0. Delta U is 0, work done is 0. Therefore, heat content is also 0. So accordingly, we have to choose the option. So this is another model of question from thermodynamics. Let us discuss one more question. So this is another numerical from thermodynamics. In a cyclic process, heat transfers are given as plus 14.77, minus 25.2, minus 3.56 kilojoules and plus 31.5 kilojoules respectively. Okay, in a cyclic process in different steps. What is the net work done in a net cyclic process? So it is a cyclic process, and first of all we should come to the point that in a cyclic process, change in internal energy will be 0. That is delta W cyclic, change in work done in a cyclic process, plus change in heat content in a cyclic process is equals to 0. It is from first law of thermodynamics only. Now, what is a change in work done in a cyclic process be expressed as minus change in heat content in a cyclic process. So this can be calculated as a sum of those values, minus of plus 14.7 kilojoules plus of minus 25.2 kilojoules plus minus 3.56 kilojoules plus 31.5 kilojoules. So on summation of these values, so we are getting, after simplification, we are getting it as a minus 17.44 kilojoules. So this is how we can solve some numericals from first law of thermodynamics. Let us see with one more. This is another question. At 27 degrees Celsius, 1 mole of an ideal gas is compressed isothermally and reversibly from initial pressure to final pressure at 2 atmosphere to 10 atmospheres. See, the question is, at a given temperature at 27 degrees Celsius, 1 mole of an ideal gas is compressed from isothermally and reversibly from a low pressure to high pressure, 2 atmospheres to 10 atmospheres. The value of internal energy change and work done are respectively. Right here, see here, work done in a reversible isothermal process. Work done in a reversible isothermal process can be given as minus 2.303 RT log V2 by V1. Log V2 by V1. But as volume change is not specified, it can be given as plus 2.303 RT log P2 by P1. Log P2 by P1. See, this is work done in a reversible isothermal process. Reversible isothermal process. Now, on substituting the values, see, here it is plus 2.303 RT log, what is the final pressure is 10 and initial pressure is 2 atmospheres. And substituting the value of R and temperature, 2.303 into 2 calories into temperature is 27, means 300 Kelvin, into log 5. Log 5 value is 0.6990. We have to remember the values. Okay. Now on simplification, we will get this value. So we will get some value. So this is a work done in reversible isothermal process. And when it comes to isothermal process, as it is an isothermal process, in an isothermal process, as temperature is kept constant, delta U, change in internal energy will be 0, or delta E is 0. Delta E will be 0. So change in internal energy will be 0 and work done will be according to this product. So this is how we can solve some questions on first law of thermodynamics, right? Let us see one more model from this. This is another question. For which change, enthalpy change is not equals to internal energy change. We can use U or E for specifying internal energy. Okay. Now, for which of the following changes, enthalpy change is not same as internal energy change? Right. See, first question is H2 plus I2 at equilibrium with 2HI. So here we have to use the relation delta H equals to delta U or delta E, whatever it is, delta U plus delta N RT. Here delta N is nothing but change in number of moles. Delta N is nothing but change in number of moles, which can be given as number of moles of gaseous products minus number of moles of gaseous reactants. Only gaseous products minus gaseous reactants we have to consider. As gaseous products are 2 and gaseous reactants are 2, for the first equation, for the first one, delta N is 0. When delta N is 0, delta H is equals to delta U. Enthalpy change is equals to internal energy change. So first option is not an answer for the given question. In second option, see, there are no gases. No gases. So obviously we can say delta N is 0. When delta N is 0, delta H will be equals to delta U. And in option C, we have one solid and this is gaseous reactants and this is gaseous products. In option C, delta N is 1 minus 1, gaseous product minus gaseous reactant, it is 0. Delta N is 0, then delta H is equals to delta E. And in fourth option, all are gases, number of moles of gaseous products are 2 and number of moles of gaseous reactants are 4, it is minus 2. as delta n is minus 2. For this case, delta H equals to delta U minus 2RT, means delta U minus something will give a value less than delta U. So delta H will be less than delta U, means delta H is not equals to delta U. So this is the option which is suitable for the given question, right? So it is fourth option. Now let us see one more question in this way from thermodynamics, right? See, this is another question from thermodynamics, right? See, the question is given about bomb calorimeter. Question is given about bomb calorimeter. For the complete combustion of ethanol in a bomb calorimeter, corresponding equation is given. The amount of heat produced is so many kilojoules at 25 degrees Celsius. Assuming ideal situation, the enthalpy of combustion delta Hc for the reaction is, we have to find out. Now let us calculate this. As the process is taking place in a bomb, see this vessel in which the combustion is carried out is said to be bomb. You are aware of that point. As it is taking place at constant volume, heat change involved in this is called as internal energy change. Heat change involved in this is called as internal energy change. Heat change at constant volume or heat at constant volume is called as internal energy. Right. Now here delta U is given as a liberated minus 1364.47 kilojoules per mole. Now what we are asked to find out, enthalpy of combustion delta H is asked. What's the relation between delta H and delta U? Delta H equals to delta U plus delta N RT. Delta U plus delta N RT. Now we are aware of this delta U value. It's given in the question itself. We need to find out delta N, change in number of moles, and substitute R value, given R value in temperature. Delta N, change in number of moles, is as we discussed gaseous products minus gaseous reactants. That equals to how many gaseous products? It is 2. Minus how many gaseous reactants? Oxygen is the only gas here. 3. It is minus 1. So delta H equals to minus 1364.47. This is delta U plus delta N is minus 1 into R value is 8.314 into 10 power minus 3 kilojoules into temperature is at 25 degrees Celsius, means 298 Kelvin. So on simplification, delta H enthalpy change, enthalpy of combustion, we will get it as minus 1366.95 kilojoules. Right? So this is how we can solve question based on enthalpy change and internal energy change. See, let us solve one more question. A piston filled with 0.04 moles of an ideal gas, 0.04 moles of an ideal gas expands reversibly from 15 ml to 375 ml. So some initial volume to final volume at constant temperature, that is 37 degrees Celsius. Right? As it does so, it absorbs 208 joules of heat. So Q value is given as 208 joules. We usually indicate heat change with the delta Q, heat with Q, right? The values of Q and W for the process will be, see, usually especially from this thermodynamics, sometimes question may be very lengthy, by looking at which students will give up in general. But this question is a very simple question where we need not solve anything. Understood? See, by looking at the question, one may feel like so much a matter is there to solve, so many values are to be determined. But in practice, it is very simple, nothing to solve, because it is an isothermal process. We have first law of thermodynamics. From first law of thermodynamics, we have delta U equals to Q plus W, right? Delta U equals to Q plus W, isn't it? Now, in an isothermal reversible process, isothermal means what? Constant temperature, no? What's meant by isothermal process? Constant temperature. as temperature is constant, delta U, change in internal energy will be taken as 0. Change in internal energy will be taken as 0. Now we can say Q equals to minus W, means heat absorbed. That means heat absorbed by the system is equal to work done by the system. Heat absorbed by the system is equal to work done by the system. What is heat absorbed by the system? Plus 208 joules. Then what is work done by the system? It is minus 208 joules. Work done is given with a negative sign, right? So that's why heat absorbed is plus 208 and work done is minus 208 joules. So this is how, without solving anything, we can answer the question. As it is an explanation, we did like this, right? So and one more thing is next question. Next question from thermodynamics we will see. So this is another question from first law of thermodynamics. A gas absorbs 200 joules of heat. So Q is given as plus 200 joules. Absorbed, no, it is given with a positive sign. And expands against external pressure. P external is 1.5 atmospheres. From an initial volume, Vi is 0.5 and V final is 1 liter. V final is 1 liter. Calculate the change in internal energy. So we are asked to find out delta U. So we know that delta U equals to Q plus W. So W we need to find because Q is already given. Work done in a reversible isothermal process is equals to minus P dV, minus P external into dV, right? Work done in this process, here it is given as minus external pressure is minus 1.5 into change in volume is V final minus V initial, it is 0.5 liters atmospheres. By substituting this over in the formula, delta U equals to 200 plus Q is minus 1.5 into 0.5. Minus 1.5 into 0.5 liter atmosphere. Liter atmosphere is 101 joules. As 1 liter atmosphere is equals to 101.325 joules. By substituting that over there, delta U equals to 200 plus minus 1.5 into 0.5 into 101 joules. So on simplification, we will get this value as 124.25 joules. 124.25 joules. So as the nearest value is in the first option, that will be the answer. So this is another question from first law of thermodynamics. Right, this is another important model which is based on calorific value. Usually student will neglect this word, calorific value. In a flow they will neglect usually. What's meant by calorific value? Energy released during combustion of 1 liter of a substance. Energy released during combustion of 1 liter of a substance. See, I am writing calorific value means heat released for the combustion of or during the combustion of 1 liter of a substance. 1 liter. Here in this question, it is given for hydrogen. Calorific value of hydrogen means heat released during the combustion of 1 liter of hydrogen is minus 12.78 kilojoules. So it is given in liters. Let us study the same in terms of moles. So we know that at STP 22.4 liters is equals to 1 mole of H2, right? 22.4 liters volume is equal to 1 mole of H2. Then 1 liter H2 is equal to how many moles? How many moles? It is 1 by 22.4 moles of H2, hydrogen. 1 by 22.4 moles of hydrogen. So 1 liter of hydrogen is nothing but 1 by 22.4 moles of hydrogen. See, let's come to this line. Heat released for 1 liter of hydrogen is minus 12.78 kilojoules means let us use the same line. Heat released for 1 liter is nothing but 1 by 22.4 moles of H2 is minus 12.78 kilojoules. Now enthalpy of formation of H2O means 1 mole of H2 will be subjected to combustion to give 1 mole of H2O liquid. So during this process, what is heat released? So for 1 mole of 1 by 22.4 moles of H2, heat released during combustion is minus 12 point. Therefore, heat released for 1 mole of H2 will be minus 12.78 into 22.4. This product will be approximately minus 286.27 kilojoules. Okay, so the nearest value will be second option. Okay, this is how we can solve questions on calorific value, right? Okay, now so far we discussed some numerical models only from thermodynamics. Actually, it has another part, that is thermochemistry. So thermochemistry deals with the second law, entropy, Gibbs energy, spontaneity, everything, right? So about the other part of this thermodynamics, that is thermochemistry part, numericals, we will discuss in our next session, right? Till then, if at all any doubts you have, you can raise it in WhatsApp group or personally.